In this video series, we'll be talking about some BGP scenario-based questions. Questions you are more likely to encounter in the interviews or maybe in your production environment as well. So, for example, one question that we have here, that a customer complains about some intermittent connectivity issue to a specific destination. You suspect a BGP-related problem. How are we going to troubleshoot this issue? Okay. So to fix this problem or to troubleshoot this issue, like we can have we can go for like some steps. We can try to troubleshoot this issue in some steps. So first thing first, like we are going to do, let's say that the destination that they are trying to reach is the destination X. So first thing that we are going to do, we are going to use the tools such as, for example, either ping or trace to see if the connectivity is okay, or is it really like flapping, coming up, going down, coming up, going down. Typically, we are going to use tools such as, for example, trace to see like where actually the drops are happening. Because once we have identified that where exactly the dropping is happening, like what is the location where the drops are there, at what point the packets are getting dropped, so troubleshooting becomes a little bit easier. Remember that you can take like, variety of approaches to troubleshoot the network. But here, when we talk about like this trace tool is going to give you like an idea, like up to this point, everything is okay. And beyond that, the connectivity issue is there. So first thing first, we should use the tools such as, for example, ping or trace or some other tools to do the connectivity testing. We should check like where the packet is exactly getting dropped. Once we found out that, okay, up to this point, everything is okay. Maybe the packet is getting dropped right at the source. Maybe the packet is getting dropped after some hops. Once we have identified that, okay, the packet is getting dropped at this point, we can begin our BGP troubleshoot. Okay. So once you have identified that the packets are getting dropped at a certain point, or maybe at the source itself, two things you need to check regarding the BGP. In BGP, whenever we need to perform the troubleshoot, we need to check two things. One thing that we need to check is the neighborship. One thing that is what we need to check is the routes. BGP is a protocol that forms the BGP neighbor relationship, or called neighborship, before it exchanges the route with the neighboring devices. So you need to check all the possible conditions. You need to see how long it's been since the origination of the neighborship establishment. Use the command like show IP BGP summary, right? Or if it is like IPv6, show BGP IPv6 unicast summary and all that. You can use variety of commands to check like the BGP neighborship. There it shows you a time referred to as like, up, down, like how long it's been since the establishment of this BGP neighborship. You can try to find out if the BGP neighborship is established or is it flapping. Because if the BGP neighborship is flapping, there could be chances, it could be a possible reason that your reachability is going up and down based on the same. So if the BGP neighborship is stable, then you can check the routes, like are we receiving the appropriate routes in the routing table, in the BGP table, and all those routes are installed in the routing table or not, right? But if the neighborship is flapping due to some reason, you need to troubleshoot everything regarding the neighbor. Like you need to find out all the possible conditions because of which the BGP neighborship cannot be established or might flap frequently, such as, for example, check for the remote errors, check for the password, check for the update source, check for ACLs. Someone might have blocked, TCP port number 179. So just do all the basic verification checks regarding the BGP neighborship. Make sure that the BGP neighborship is up and running. Then when it comes to like checking if the routes are stable or not, then you can use the command either show IP BGP, or you can check like show BGP IPv4 unicast and all that. Like if you want to check for the other address family, you can use the command. To validate if the routes are stable in the BGP database and in the routing table or not, right? Oh, we might have performed like maybe the route to reach to that destination is not there because we have applied some sort of like filtering based on ACL, based on prefix list, based on like AS path list, communities, different like ways are there in BGP that we can use to perform the route filtering. So maybe we are not even receiving the route to reach to that particular destination, right? So try to troubleshoot all the things regarding the routes. Why a certain route is not available in the routing table, and if the route is flapping or what. Because if the route is available, but it is flapping, again, intermittent issue, connectivity problem you might face. We can implement features such as, for example, like once if the route is flapping, then we can enable the features such as, for example, BGP dampening, which is going to dampen the route until it gets stable. So we can also check for like, dampening configurations. We can also check for route filtering parameters, right? We can, when we are troubleshooting the neighborship, we can also validate the timers and everything, because sometimes if we misconfigure the timer, you will notice that the BGP neighborship will come up and then go down, come up, go down. If the timers like the keep alive timer and the whole timer is not correct, then the BGP neighborship might be down. Also make sure like route selection process, like, BGP best path selection process or route selection algorithm that we have. We can apply a variety of attributes to influence BGP best path selection process. Typically, we use things such as, for example, route map to influence like incoming routes, outgoing routes, and all that. Sometimes what happens when we apply the route map, we forget to mention the keywords such as permit any at the end, because of which routes might not be available in your routing table. So also like, make sure that you have enabled proper route map with proper, statements, so that the routes are installed in the routing table. If you have done some manipulation with the help of the route map, make sure the manipulation such as, for example, changing the MED, multi-exit discriminator, changing the path attributes, any path attributes such as, for example, MED or the AS path list or the origin code, make sure that the route manipulation is done properly, right? There could also be a chance of routing loop. So make sure like the routing loops are not there. When you are doing the trace, in the ping and trace, when we are doing the ping and trace, make sure that the traffic is not basically hitting repeatedly between two or more devices, right? So in this situation, you might also see that the routing loops might also cause the drops in the network. So make sure that the routing loops are not there, right? Also, what else we can check? We can check for like in this situation, we can check for like congestion. So sometimes what happens like because of the network congestion, the packets might get dropped. So what we can do, next thing that we can check for is the congestion in the network. So there are chances like the network congestion is there, and because of the network congestion, packets are getting dropped. That could also be a reason. That could also be a case. So we can use a variety of tools such as, for example, SNMP. We can use tools such as, for example, NetFlow. We can use these tools to check the flow of the network. We can use these tools to check the congestion in the network. We can monitor the network traffic and we can check for congested links as well, right? Also check for like any hardware failure. Like you might have like, for example, a failed hardware in the network. You might have, let's say, for example, the software has crashed or something like that. So for hardware and software issues, you might also need to see, because maybe you have just installed a new software onto your device, and in that software, the BGP pairing is not getting stable due to some bugs or so. So you should also see for like, hardware and software related issues. So maybe a router that you have installed, it is faulty. Maybe the cables like that you have used to connect two or more devices, like routers or switches or whatever, maybe those cables are not performing well, or maybe the network interface card that we have where the cable is connected, the pins of that network interface card is not okay. It can also, cause an intermittent connectivity issue. So these are some general, issues that general suggestions that are there that you can use to check and find why the intermittent connectivity issue is there. When it comes to BGP specifically, based on what type of topology is there, when it comes to BGP, mostly you need to troubleshoot like if the BGP neighborship, and you need to troubleshoot if the routes are there in the BGP table and in the routing table. If the neighborship is stable, if the routing issue is not there, if you are having the routes throughout the path from source to destination, then some other problem might be there causing the intermittent connectivity issue, not the BGP one, right? So check for like CPU utilization and as well, because BGP is a protocol that consumes like a lot of resources. So you might also need to check if like the CPU utilization on the device is not going very high because of this BGP. BGP is a very heavy protocol. It can also result in like high CPU utilization on the device. Because of that, drops can be expected. So some intermittent connectivity issue can be there because of that as well. So these are some general, suggestions that you can take to fix this problem of intermittent connectivity issue. These solutions, these recommendations are specifically from the BGP point of view. Some other issues can be there as well. Your organization is merging with another company, and you need to establish the BGP pairing between the two networks. Outline the steps you would take to ensure successful BGP pairing setup. Okay. So this is a simple question where we need to like merge two or more like companies together as well. So here at the moment, let's say we have a company called X, and then here we have a company called Y. And basically these two companies have a few routers at the edge, and the merger has happened. Like these two devices has to merge together to represent like a big company. So, and what we need to do, we need to configure the BGP neighborship between the same. So first of all, like we need to determine like what type of BGP design we are going to have, like single home, multi-home, single multi-home, dual multi-home. We can have different types of design. Maybe we have two routers at the company X and two routers at the company Y, and we might want to go for the full mesh kind of design, or we might want to have like partial mesh kind of design, single home, single multi-home, dual multi-home. So first of all, we will plan like what type of design we are going to have when it comes to connecting like these two devices, these two companies, these two organizations, if I say. Then we are going to get the information. So first of all, what type of design we are going to have, like single home, single multi-home, dual multi. Second thing, we are going to find out here, like the subnets, the IPs that we will use to form the BGP neighborship. Of course, it could be like eBGP, it could be like iBGP. If you want like everything to be part of the same BGP autonomous system, then we can configure the iBGP neighborship. If you want like to have eBGP running between them, then that is also okay. Maybe this company is already running BGP AS100 and this company is already running the BGP AS200. So in between them, we can have this eBGP neighborship. Or maybe when the merger has happened, we might want to use the same BGP AS in between the both. So if considering that here we are going to configure eBGP neighborship, we are going to find out all these necessary parameters, such as, for example, the IP address, AS number, what routing policies we need to apply, right? And other BGP configurations, such as, for example, eBGP multi-hop and all that, like TTL security, or like password, all the necessary things we are going to gather. We are going to collect all the necessary information that will be required to form the BGP neighborship between two devices. Right? Now, so we are going to find out like what kind of design it is going to have, like single home, single multi-home, dual multi-home. Then we are going to have like the information about the IP, AS policies. Is it going to be like eBGP, iBGP? If it is eBGP, eBGP multi-hop, TTL security, passwords, and all that thing we can configure. Then, like once we get all the necessary information, then in the third step, we are going to configure these routers. Configure these like edge devices. We are going to configure BGP. We are going to configure border gateway protocol on there. And the BGP, we are going to configure with the appropriate configurations that we have got in the second step. Once done, we will verify that the BGP neighborship is up by using the command show BGP summary, show BGP IP4 unicast summary. By using certain commands, we are going to validate that the BGP neighborship is up and stable, because flapping might also happen. So make sure that the BGP neighborship is actually stable as well. Right? We can do the connectivity test again using the tools such as, for example, ping and trace. So in verification, we can use the tools. We will verify the BGP neighborship. Then we can use the tools such as ping and trace to see if the packets are actually flowing from one point to the point or not. And next, Next, what we can do, next we can, in the fourth step, in the next step, what we can do, we can now optimize the BGP neighborship as per our requirement. We can optimize the flow. We can optimize the flow as per our requirement. By optimization, what I mean, I might want to send the entire traffic from here, but receive from here. We want to configure some sort of traffic engineering based on the BGP configuration. So we might want to do that. So we are going to optimize the flow by applying certain policies between these devices. We can apply the policy to control how traffic exits and how traffic enters in the BGP autonomous system. Right? We can also perform, we can filter all the unnecessary prefixes with the help of variety of route filtering mechanisms that are available, such as, for example, ACL, prefix list, AS path list, and the others. Once done, once all is done, once you have, then again, we are going to do some verification using a ping trace tool. We will validate all the configurations that we have done. We will make sure that the traffic is being sent from the appropriate path and the traffic is being received from the appropriate path as well. So once we are going to validate all that information, then at the next step, we can also implement a certain, like, security related policies, such as, for example, we are going to enable SSH so that we will be able to manage these routers remotely as well. Once the neighborship is there, we are going to configure some passwords for the BGP neighborship, TTL security, all those security related policies we can configure as well. Right? So first thing, to summarize, first thing, we are going to decide what type of design we are going to have. Then we are going to collect all the information that is required, information such as like IP, AS number, any particular password that we need to configure, or the routing policies that we need to configure. We are going to collect all that information. Then we are going to use the configuration command to configure the BGP. Once the BGP is configured, we are going to verify the BGP neighborship. We are going to verify the BGP neighborship by variety of commands. Once we have verified the neighborship, we are going to exchange the routes and everything. Once the route exchange process is done, then we are going to do the ping and trace to validate the end-to-end connectivity. And then at the end, we are going to monitor the BGP neighborship, and maybe we are going to optimize the BGP neighborship as per our requirement. By optimization, we mean that once the neighborship is there, what we mean, like we might want to send the traffic from one of the router, but might want to receive the traffic from the other router. So some sort of traffic engineering we might want to do as well. So those things we can implement here. And once done, final verification. After the final verification, again, we are going to use the ping and trace to cross-check, like if the traffic is following the intended path as defined in our policy or not. Remember, when the migration, like maybe the company that we have here, company Y, is already running some BGP autonomous system, and you want to migrate from one autonomous system to the autonomous system. You can use the concept of like confederation autonomous system, which is very useful. Like if you have, when the merger of two or more company happens, they can retain their own autonomous systems, AS200, AS100, and they can be made of part of a big confederation autonomous system. So we can also use the concept of like confederation autonomous system, where we can define like a confederation AS, config AS in between the devices, or rather than changing the AS of one autonomous system to something other. That thing can also be done. Right. So these are a few things that we should take care of. That these are the few things that we should consider before migrating or before merging one organization to the other organization. We notice that one of our BGP peer is advertising large number of routes, causing instability in your network. How would you handle this situation to maintain this stability? It's very simple. To control like what routes can be accepted by the router in border gateway protocol, we can use variety of like routing policies. So to control this problem, to fix this problem, what we are going to do with that particular neighbor, let's say, for example, the neighbor is router number 1. Let's say the router number 1 is advertising large amount of routes to router number 2. What we can do here, we can implement variety of policies on router number 2 in inbound direction. If we have the access to router number 1, we could have applied the policy in the outbound direction as well. But since considering that we don't have the access to router number 1, because it is on the remote end, we have the access of the router number 2. What we can do, we can apply a variety of routing policies in the inbound direction. In this policy, we can filter, we can use these route filtering policy to control like what prefixes are accepted and what prefixes are not accepted by the router. So in the route filtering policy, we can use things such as ACL, we can use things such as prefix list, we can use AS path access control list, we can use community list, we can use route map, we can use variety of techniques to perform the route filtering. So what we are going to do, let's say, for example, we are going to use the prefix list. So we are going to match the desired prefixes. We are going to accept those prefixes, and I'm going to block the rest of them. And then we are going to apply this prefix list in the inbound direction with that neighbor point of view. So when this neighbor advertises the prefixes, route filtering will take place, and except for all the prefixes that we want to receive, rest of the prefixes are going to be blocked. We could have also used things such as, for example, AS path ACL to control like what certain prefixes with these ASs in the AS path list are accepted, and other than all the prefixes are going to be dropped. So it's easy, like to control this, to control what routes can be accepted, not, we can implement these routing policies. Specifically, we are going to implement this route filtering policy. In this route filtering policy, what we are going to do, we are going to control, we are going to permit all the our desired prefixes, and we are going to deny all the rest of the prefixes, right? That we can do. Once done, once we have implemented all these policies, do not forget to monitor. Do not forget to monitor and optimize again to validate, like, what. So once we have applied the policy, monitor, use the variety of commands such as show IP BGP summary, show IP BGP all, use those commands to check if all the routes that we wanted to receive are available in the BGP table and in the routing table. If the routes are not available, then change the ACL, change the prefix list, do the necessary changes in the access list or prefix list to control what routes are to be accepted. Right? So once we have applied all that, don't forget to monitor the BGP table and the routing table to confirm that the desired routes are available. Also, like whatever traffic is being sent or received, you can also influence the outgoing or incoming data, again, using the same policies that we have discussed in the previous recordings. So we can implement like variety of policies to influence like incoming or outgoing traffic. We can implement those policies to control how the traffic exits or enters in our autonomous system. Right. So generally what we are going to do to control what routes can be accepted or not, we can implement these routing policies. These policies can be applied in the inbound direction or the outbound direction. But since we wanted to do everything at our end, we are going to apply these policies at our end only. So this is like, how to filter. We can use the filtering based on like these different routing policies. A customer want to implement redundant BGP design to improve the network stability, explain different options available and their pros and cons, right? So basically here we are talking about like different options that we have in BGP from the design point of view. So first and the most common deployment that we have is referred to as the single homed design. In the single home design, basically where we have one, let's say, for example, router at the customer end and the other router at the provider end, like where we have like only one router, one link between single homing connection between like customer and provider. Like this kind of deployment is what we are going to refer to as the single homing design. So customer has a single connection to the provider. That is what we refer to as the single home. We can add like one more link here, like one more cable can be connected for the redundancy purpose, but then it is going to be a different design. So here, like single homing design is going to look something like that. Now, the advantage of this design, like this is one option that they can implement. The advantage of this design is that it is very simple. It is very like easy to implement and handle actually. That is the advantage of this design. And the disadvantage of this design is that there's no redundancy. So if this link goes down, then the entire connection is going to be down from the customer and provider point of view. More importantly, this is not a very common deployment that we see, because here, in this situation, since we have only one link, see, we use BGP typically when we are concerned with the routing policy, typically when we want to send the traffic from one path, receive the traffic from another path. Basically, when we want to do some sort of traffic engineering or so, then generally we concern about we use this border gateway protocol, BGP protocol. Now here, since we only have one link between the provider and customer, what you could have done, just the default route here, and that default route that we have configured pointing towards the neighbor router, I can either use the command such as default information originate, or some way you can use some way to flood that default route in the customer environment. The point is that instead of using BGP between this router 1 and router 2, between this customer and provider, since there is only one link, we will not be able to do any path manipulation, path influence, or anything. So it actually doesn't make any sense to configure like border gateway protocol between the devices. Here, just the default route, maybe just netting here, configure NAT, like advertise the default route in the internal network. That will be sufficient, right? So easy to implement, easy to maintain, but redundancy is not going to be there. That is a problem. Second design that we have is called dual home. In the dual home design, what we have multiple connections. We have multiple connections from the customer to the provider side, right? So in the dual home connection looks from the design point of view, the dual home connection is going to look something like that. Like here, we are going to have in the dual homed connection. In the dual homed connection, we are going to have like one ISP. Here we have dual routers, and here in the customer side, we can have like one or two routers. The key point here in the dual homing is that you are still connected to the single ISP. Multiple links can be there, but still, like we are connected to a single ISP. In the dual home design that we have here, dual home design, we get the advantage of redundancy. So if this link goes down, this link can be used. If this link goes down, then this link can be used. So in the dual home, we can, first of all, the advantage that we get is the redundancy. We get the redundancy between the customer and the provider router, between the customer and the provider network. That is the advantage. Second, we can achieve like either load balancing, where the entire traffic can be load balanced between two routers, or we can go for like one link as the active and one link as the standby link. We can use variety of BGP path attribute to control, like this link is going to be used to send the traffic and this link is going to be used to receive the traffic. So some sort of, active and standby redundancy can be there, or we can use both of the link to send the traffic and receive the traffic as well. So that is going to be like advantage. We have great redundancy here. Like the problem that we are having here, the disadvantage, the cons that we have here is that it is comparatively going to be like complex to manage, understand, comparatively complex to implement also as compared to the single homing design. It is complex. It is complex to handle and manage. Second challenge that we have, second limitation that we have in this design is that we are still connected to the same ISP. So if something happens from the ISP point of view, not like, link point of view, if something happens from the ISP point of view, then anyway, both the connections are going to go down. So dual multi-home connection adds the redundancy, But it also, like, since we are connected to the same ISP on both the link, if ISP goes down, then the connectivity will go down anyway. So we can implement this kind of design if only one ISP is available, or we can add some redundancy by adding multiple routers as well. There are variations of this design as well, where the links can terminate on the same router, on the customer end, link can terminate on the other router. We can implement as per our requirement. Third design that we have is referred to as the single multi-homed design. So in the single multi-homed, if they want to implement the single multi-homed, in that case, we are going to have like multi-homed. Multi-homed basically means like multiple ISPs. So this is one service provider. This is the second service provider. This service provider that we have here, router 1, router 2. Here we have like at our home, at our customer side, we have router number 3. So this kind of design is what we are going to refer to as the single multi-home design. In the single multi-home design, we have multiple ISPs involved. Again, it is going to add some redundancy in the network. So which is the advantage? If one link goes down, then the other link is available. That is the advantage. It is going to be comparatively complex to manage, handle. That is a disadvantage, if I say. The advantage with this design is that we are now connected to the multiple ISP. So if something happens to the first ISP, still like the second ISP is available to send and receive our traffic. Again, same thing, we can send either entire traffic from like these two paths. We can send this, we can use this link to send the traffic, this link to receive the traffic. Those things we can still achieve in the single multi-homed design. Multiple ISPs is there. Multiple ISPs is there. That is going to add the advantage. In this multi-homing design, we are going to have redundancy as well as some sort of high availability as well. And the best that you can go for from the design point of view is going to be dual multi-home. The dual multi-homed design that we have here, in this case, what happens, like we have two, let's say, for example, router at our customer side, and we have multiple ISPs. This is like ISP number 1. This is ISP number 2. And here we have a router. Here we have a router. And we are connected with dual links to both the ISPs. Again, variations are there of all these topologies. So in this case, this is like kind of like we have the best redundancy and high availability actually in here, as you can see. But again, it is going to be complex, very complex, I would say, to configure, manage, implement, all those things are going to be complex. But when it comes to redundancy and high availability point of view, this is going to be the best design that they can go for. Right? They can choose like one link to send the traffic, one link to receive the traffic. This is our active one. Then if this goes down, then this router will become the active. So send the traffic, receive the traffic. They can implement variety of routing policies to influence how the traffic is sent and received in the autonomous system. Right? So the dual multi-homed is going to be the best option. So to summarize, they can either go for like single homed, not recommended for BGP, then dual homed, then single multi-homed, and then we have fourth design that we have is the dual multi-homed. So this is going to be the best one. If they don't go for this, they can go for this one as well. Since multiple ISPs are there, we will have both redundancy and high availability. Dual multi-home scenario can also be used with the BGP. But remember that since we are still connected to the same ISP, if that ISP goes down due to some reason, then still the challenges you will face. So they can like go for any of these design as per their requirement. Scenario that we have here says that a customer wants to implement the route reflector in their BGP environment to simplify the route propagation, explain the concept of the route reflector and how they differ from the configuration. Right. So in BGP, especially when we are talking about like IBGP, there is a rule that is referred to as the IBGP split horizon. This BGP split horizon rule says that the route that you have learned from one of your IBGP neighbor, they are not advertised to other IBGP router. Considering that everyone belongs to the same autonomous system number 100, means that everyone belongs to the AS number 100. This is the route 1.1.1.1 gets advertised to the router number 2. Since router number 2 receives the route from the router belonging to the same AS number, this will be like IBGP neighborship and IBGP route. This router cannot advertise the route to the other IBGP neighbor. So IBGP split horizon is a rule that says that the route learned from one IBGP neighbor are not advertised to the other IBGP neighbor. But if you want to like have the end-to-end connectivity from like 1.1.1 to 3.3.3, somehow this router 1 must know about 3, somehow this router 3 must know about 1.1 subnet. So what we can do, since in BGP it is possible that we can form the indirect neighborship, I can configure a neighborship between router 1 and router 3, and I can exchange these routes directly as well. So over this indirect peering, router 1 and router 3 can exchange the route to each other, and then of course they will be able to do the ping and trace. The challenge here, the problem here is that if there are like 2-3 routers, then this approach is okay. Like this full mesh neighborship requirement that we have is okay. If 3-4 routers are there between 3-4 router, we can configure the full mesh BGP neighborship. But when we have like a lot of routers, 7-8 routers in our IBGP environment, and we want to propagate the routes from one point to other point, then configuring this full mesh neighborship might not be a very good idea. It is possible, still possible, but it is going to be like too much time consuming process. Right? So if we have like 7-8 routers, then the problem might occur. If let's say, for example, 8 routers are there, then n-1 divided by 2 number of neighborship has to be created, has to be built. So to overcome this BGP split horizon rule, BGP split horizon rule is there to prevent any potential loop in the IBGP environment. In case of eBGP, we have this concept called AS path list. So if the AS path list contains your own AS, you are not going to accept that prefix. That is that is eBGP loop avoidance mechanism. When it comes to like IBGP, in case of IBGP, this IBGP split horizon rule is used for the same. Now, the point here is, if you don't want to implement the full mesh BGP neighborship, you can also go for this thing called route reflector. Basically, what I can do, I can configure this router as the route reflector. It is going to receive the route and reflect the route to the other IBGP neighbor. So route reflector is the device. Route reflector is the device that reflects the route from one IBGP to other IBGP neighbor. Right? Now, this route reflector, since we are using this route reflector concept to bypass or to override this IBGP split horizon rule, the problem is it may lead to a routing loop. It may lead to this routing loop. So what we can do, actually we don't need to do anything. When we use this concept of route reflector, or when the routes get advertised to the neighbor router, automatically this route reflector is going to add 2 things. One is called like originator ID, and one is called something called cluster ID. So concept of originator ID and cluster ID is added when the routes get propagated to the neighbor router. And because of these 2 things, originator ID and the cluster ID, loops don't occur even in the IBGP environment, even if you have used the route reflector concept. So originator ID is going to be the router ID of the router that has originated the prefix in this BGP environment, IBGP environment. And cluster ID is basically, you can consider this cluster ID as the similar to the router ID, but from the route reflector point of view. So either we configure this cluster ID by ourselves, otherwise it will be chosen exactly the same as the router ID is chosen. Anyway, so this device is going to have a cluster ID, it is going to advertise that cluster ID and the originator ID to the neighbor router. Then this router, if we have like more than 3 routers in the domain, maybe router number 4 is also there. And if we want that the router 4 should advertise the route to the neighbor router, then this also has to be configured as the router reflector. Originator ID will remain the same. This router number 3 is going to add its own cluster ID before propagating the route to the neighbor router. So in that situation, what will happen? Like this device is going to receive the prefix with the originator ID 1.1.1 and the cluster list 2.2.2.2 and 3.3.3.3. Those two attributes that we have, originator ID and the cluster ID, they are used to, in fact, control. They are used to form, they are used to control like if the routes are going to be accepted or not. So if due to some reason the prefix gets advertised back to router number 1, router 1 is not going to accept it because the originator ID is same as your own router ID. And if somehow the packet reaches to router number 2 or router number 3, they will also not accept it because cluster list contains your own cluster ID. What exactly is a cluster? Router reflector client and servers are referred to as the cluster. So we can configure router number 2, configure router number 3 as the router reflector devices, and then they will be responsible to advertise the route to the neighbor router. So in the router reflector, we have a device called router reflector, then we have router reflector client, and then we have router reflector non-client. So if we have a diagram such as, for example, router 1, router 2, router 3, router 4, something like that, router number 5, and let's say we configure this as the router reflector. How can we configure this as the router reflector? I will go on this router. I will use the command under router BGP configuration, neighbor IP, router reflector client. As soon as I configure the command neighbor IP, router reflector client, this will become the router reflector for this client. Neighbor IP, router reflector client is the command that we can configure to enable the router reflector functionalities there. Now the rule is, if you receive a route from your client, you can advertise the route to the client. In fact, you can advertise the route to a non-client as well. What is a non-client? Non-client is a device for which we have not configured this command, a router reflector client. So if you receive the route from the client, you can advertise it to the client and to the non-client as well. If you receive the route from the non-client, then you can advertise it to the client. But if you receive a route from the non-client, you cannot advertise that route to another non-client. So non-client to non-client, routes are not advertised. Rest from the client to client, client to non-client, non-client to the client. From all these devices, like the routes get advertised. And while the routes are getting advertised via the router reflector, the concept of cluster ID, cluster list, if I say, and the originator ID is added in the prefix so that the routes don't form like any loops in the network. Now, the limitation of this router reflector is that this is a router reflector. It has advertised all the route to router 3. Now I want router 3 to advertise the route to router 4. So I will need to configure this as the router reflector as well. Then there is router 5 here somewhere, like router 5, router 6, router 7 is there. So all the routes are getting advertised to router 4. Then I also need to configure this as the router reflector to advertise the route to the neighbor router. Point is that more than one router reflectors will be required in your IBGP environment if you have a big topology. So generally what we do from the design point of view, let's say we have like a lot of devices here. A lot of devices are here. Let's say, for example, a lot of devices are here, and this is the physical connectivity. This is connected to some external autonomous system. What we do actually here, we choose 1 or 2 devices as the router reflector, any 2 device. Any 2 device we are going to choose as the router reflector, and we are going to form our neighborship with that router reflector. So everyone, like for example, this device is going to form the neighborship with this router reflector. Every device is going to form the neighborship with the router reflector. The way we deploy this router reflector is that this device is now going to form the neighborship with this router reflector. This will form the neighborship with this router reflector. This is going to form the neighborship with this route reflector. Then this is going to form the neighborship with this one as well. This is going to form the neighborship, like here, the neighborship is there, here the neighborship is there. So there is no neighborship between like these non-clients to each other, but everyone is going to form the neighborship with this route reflector. So the routes will be learned, routes will be advertised to the route reflector, and route reflectors are going to advertise these routes to the rest of the network. While advertising, we can do that path manipulation and all those things as per our requirement as well. Right. Now, if you have a very big network, if you have, let's say, for example, a very big network, in that situation, like this concept of route reflector might not be a very good idea. You can go for this thing called configuration. What we could have done, instead of like, configuring these devices as the route reflector, instead of configuring the full mesh neighborship also, what we can do, we can divide this big BGP network into smaller networks, such as these two devices are now going to be formed. They are going to be part of a sub-autonomous system. We can break this big autonomous system in BGP into smaller autonomous systems referred to as the sub-autonomous system. Then this is going to be sub-autonomous system. Then this is going to be another sub-autonomous system. So we can break the BGP neighborship, like we can break this big autonomous system into smaller autonomous systems, and these are what we refer to as the sub-autonomous system. So overall, this overall network is now going to be referred to as the confederation autonomous system. Confederation allows us to break a big autonomous systems into smaller autonomous system. So this is one sub-autonomous system, 100. This is another sub-autonomous system, 200. This is another sub-autonomous system, 300. So IBGP, confed IBGP, confed EBGP, confed EBGP neighborship can be formed. So we don't require any route reflector in that. If we had like multiple devices, let's say for example, here we had like one more device here in this. So I could have configured like this device as the route reflector. So route reflector with the configuration will also work. So route reflector differs from the configuration. Why? Because in the route reflector configurations, we have like one or two route reflectors in the network. Everyone forms the neighborship with them, and then they advertise the routes to the rest of the network. Basically, in the IBGP environment, it is the responsibility of the route reflector to reflect the route from one to another. While in the confederation, the entire autonomous system is broken down into sub-autonomous systems, and the routes get advertised from one sub-autonomous system to other sub-autonomous system. So based on their choice, if they have like medium to small scale network, they can go for this concept of the route reflector. But if they have like big network, then they should go for the confederation autonomous system. This is the difference between the confederation and the route reflector. Both the techniques that we have are there to avoid that IBGP split trigon rule or bypass that IBGP split trigon rule so that the routes can be advertised from one point to other point.
The next question that we have here, it says that one of your BGP peer is experiencing high CPU utilization, leading to slow convergence and potential instability in the network. How would you identify the cause and implement a solution for this problem? Now we know that BGP is a protocol that consumes a lot of resources in terms of RAM, in terms of CPU. So someone like is facing the same like high CPU utilization. So we need to rectify the issue. We need to find out a possible solution for the same. So first thing first, what we are going to do, we are going to gather some information regarding like why that CPU utilization is high. So first thing what we can do, we can execute the commands such as show processes CPU. Again, history, utilization, some other commands. You can do a question mark to find out. So first of all, we are going to execute the command such as show processes CPU to find out like which process on the router is consuming like most resources. If let's say, for example, BGP is consuming most resources, then we can execute the command such as, for example, show IP BGP summary to find out like how much resources BGP is consuming and most of the resources are going in exactly like where, like for example, maintaining the network information, maintaining the path attribute, like resources are being consumed exactly where. We can find out that thing from show IP BGP summary. We can execute these commands to verify the logs and everything. We can verify the processes running on the router. We can verify the information regarding the BGP, and of course the logs that we are getting, like CPU high utilization logs that we are getting, we can also check those logs to find out like exactly which process is causing more CPU utilization onto the device. Then what we can do, we can check like BGP configurations. We can use like show run pipe section, router BGP, show IP BGP summary, show IP BGP all summary. We should check the BGP configuration, and in that BGP configuration we should check like if we have done all the configurations properly or not. Sometimes what happens, like due to some misconfiguration also, peer like BGP neighbor relationship doesn't get formed, but messages will keep coming, causing high CPU utilization and all. So we should check the BGP configuration. We should validate. We should see if all the BGP configurations are okay or not, and then we can confirm from the command like show IP BGP summary. We can see if the BGP neighborship with all these neighboring devices is established properly or not. We might have done some changes, so we also should check for those changes that we might have made to find out any potential causes of the problem after the changes. If you do some recent changes, like some recent changes can also cause problems in the network. So from different resources, such as for example logs, such as for example these BGP outputs, such as for example those CPU processes, CPU utilization, like those commands, you are going to gather all the information, and then you are going to check for the BGP, check the BGP neighborship, check if the BGP neighborship is stable or not. Because what happens, like if your BGP neighborship is not stable, if it is flapping, it is going down, coming up, going down, coming up, going down. So in that situation also, you might see high CPU utilization, because every time the neighborship goes down, the device needs to flush all the routes information, clear the neighbor from the neighbor table, then it is coming up again. Messages, BGP is going to use those messages like open message, keep alive message, update message, notification message. The BGP will use those variety of messages to again create the neighborship, and so we should also check if the neighborship is in a stable state or not. Unstable BGP pairs also causes the problem. Also check for like the routes that are being advertised from the neighbor router. Maybe your device doesn't has a lot of resources to handle that much amount of routes, so check for the limit that you have onto the device regarding maximum number of routes that it can install. Also, you should actually see if the neighboring device is not, or is it advertising the updates very frequently, like frequent BGP updates. If the updates are being advertised very frequently, then also CPU utilization will definitely go high. Right, so if there is any errors in the BGP neighborship, or if the neighbor is advertising the updates way too frequently, in that situation you will also notice that the CPU utilization will in fact go high. Right, what we can do to solve this, we can configure variety of policies. We can configure the policies for that particular neighbor, that when you send me the update, I'm going to only accept these much routes, I'm not going to accept the other routes. I'm going to configure the policies regarding, let's say for example, redistribution. I'm going to configure the policies regarding the route filtering. I'm going to configure the policies to make sure that only proper devices, only authentic devices, only authorized devices are allowed to form the BGP neighborship with me. Right, we can configure variety of policies to make sure that our BGP neighborship is okay and our limited amount of routes are being received from the neighbor router. Okay, what else? You should also check on timers. A BGP uses like timers such as, for example, keep alive timer. Keep alive timer is like 60 seconds, and hold timer, which is like 180 seconds. So you should also check the timers. If the keep alive timer and the hold timers are not configured properly, then also your neighborship might flap, and based on which like your CPU utilization will go high. Right, so check for those things as well. Also to limit how many number of resources, how many number of prefixes you can receive or send, we can configure things such as, for example, summary, which is what we refer to as aggregation. We can configure route summarization or aggregation onto the router to control, like instead of sending n number of prefixes, I am just going to advertise 1 or 2 or maybe 3 summary prefixes. So to control the limit, to control the route advertisement, to put a limit on the route advertisement, we can also apply the policies, of course, outgoing policy, incoming policy, but we can also configure this route summarization, route aggregation as well. In short, you need to make sure that fixed amount of routes that are required by your router are the only routes received on the router. Rest you need to drop or ignore using some of the policy. Right? So that is also one thing you can check. Design. Your design might include things such as, for example, route reflector. Your design might include things such as, for example, configuration. If you have not configured your BGP design in a proper manner, it might cause a potential loop in the network. And if the packet gets stuck in the loop, of course, the CPU utilization will go high in that case as well. So you should also check for any potential loop because of those incorrect route advertisement, maybe in the route reflector environment or in the configuration environment. So check for those things as well. Use some monitoring tools such as, for example, SNMP monitoring tools. Use some sort of monitoring tool to get the information on the updates that you are receiving onto the router, which might cause high CPU utilization as well. We can configure if a route is getting advertised, then getting dropped, then getting advertised, getting dropped again and again. We can configure things such as, for example, BGP dampening. BGP dampening is a concept that allows the BGP router to not advertise a certain prefix if it is flapping again and again and again. Right. So we can also configure BGP dampening to stop the propagation of flapping prefix and advertise the rest of the prefixes. That thing we can configure. The hardware, where we have configured the border gateway protocol, where we have configured the BGP hardware resources, we must also check. Maybe your device doesn't has enough RAM, your device doesn't has enough CPU or resources, which and you are receiving like 1,000, 2,000, 10,000 number of prefixes, then also your CPU utilization or resource utilization will go high. So you need to make sure that you have sufficient hardware resources available on the device to handle constant BGP updates or to handle BGP messages, right? So hardware resources you should also check. So these are things that we can check to control, like to find out like why the CPU utilization is going high. And what we can do, we can implement variety of policies such as inbound route filtering policy, outbound route filtering policy. We can configure things such as ORF. We can configure things such as we can adjust the timers. We can check and adjust the timers accordingly. We can control like who can form the neighborship with us, who cannot form the neighborship with us, who can send the updates, who cannot send the update. We can do all those things to make sure that we have formed the neighborship with only appropriate routers and we are receiving all the necessary prefixes only, and rest all the prefixes are getting dropped. These are some things that you can use to these are some points that you should consider if your device is facing high CPU utilization and because of that you are facing challenges. So the next question is that a customer wants to implement a route reflector in their BGP environment to simplify the route propagation. Explain the concept of the route reflector and how they differ from the configuration. Okay. So we can implement BGP in two flavors. We can implement something called I-BGP. We can implement something called E-BGP. When we configure BGP between two routers that belong to different autonomous system, 100 and 200, then this is what we refer to as E-BGP, external BGP. These routers are E-BGP, neighbors, peers, speakers. And when we implement BGP within the autonomous system, like both the devices, both the router belong to the same autonomous system, when we configure the BGP here, this is what we refer to as the I-BGP. In eBGP, there is an attribute called AS path attribute, which is used to prevent any potential loop in the eBGP environment. In case of iBGP, there is a rule called iBGP split horizon. IBGP split horizon rule says that a route that you have received from one of your IBGP neighbor, you cannot advertise it to another IBGP neighbor. So if this is like 1.1.1.1/32, this route was advertised to router number 2. Router number 2 can receive and install that route in its table, but it cannot advertise that route to the neighbor router. Right? So that is what we refer to as the IBGP route reflector. To overcome this IBGP split horizon rule, which is there for the loop prevention, because if this route gets advertised to the neighboring router, then neighboring router advertises it to the next router, then it advertises it to the next router, and then it comes back to router 1, it might cause a loop here as well. So to deal with this IBGP split horizon, like, because if routes are not getting advertised up to router number 3, this router number 3 will never be able to know about this subnet. As a result, traffic will not pass. So to handle this, to overcome this IBGP split horizon rule, like to advertise the prefixes from here to all the way to all the routers in the network, what we can do, we can either go for IBGP full mesh, which means like every IBGP router must be configured as a neighbor with the other router. So if we have, let's say, for example, 4 router, this, then this, then this, then this, like all these devices will form the BGP neighborship. IBGP full mesh neighborship will be required to advertise these routes from one device to all the other devices. Second thing what we can do, we can use this concept called route reflector. If you don't want to use this IBGP split horizon, what we can do, we can use this concept of route reflector. So I can configure this device, router number 2, for example, as the route reflector. So this device will receive these routes and it will reflect those routes towards the other devices. Then I will configure this device as the route reflector as well. So this device will receive the route and reflect the route towards the other devices. So route reflector is the router that reflects the route from one of the IBGP router to other IBGP router, while maintaining the loop-free environment. Loops will still not form. So now how this route reflector actually works. In route reflector, we have the concept of route reflector server. We have the concept of route reflector client, and we have the route reflector non-client. So let's say, for example, router 1, router 2, router 3, router 4. There are 4 routers. All belongs to the same AS number 100. And here we have a subnet 1.1.1.1/32. So this subnet information will be advertised to the neighbor router. Router number 2 will receive it, and router number 2 will not advertise it to the router number 3. So we need to configure it as the route reflector. How can we do that? We will go under the router BGP configuration. We will say neighbor IP, such as, for example, for router 2, this is my neighbor. So neighbor IP, whatever it is. And then I will use the command after that, route reflector client. As soon as I use this command, this router becomes client and I become server. So I become the route reflector. This router 2 becomes the route reflector for this client, router number 3. We don't need to configure like I am the route reflector or something like that. This device will become the route reflector and this will become the client. And the remaining devices, such as, for example, router number 1, it will be non-client, right? It will be non-client and all that. Now the rule is, if a route reflector receives the route from the non-client, it can advertise it to the client, and it can, like this non-client routes received from the non-client, it can advertise it to the client, and it cannot advertise those routes to the other non-client. So this will okay, this will be not okay. Let's say, for example, here we had another router. Here we had router number 5, and I just configured router number 3 as my client. In that situation, router number 2 will receive the updates from the non-client. It will advertise it here, but it will not advertise that to another non-client. So non-client to non-client routes are not reflected. Non-client to client a routed is reflected. And here, let's say, for example, here it is like 3.3.3.3. Let's say from here I receive a route. So when I receive the route from the client, route reflector can advertise it to the client and it can advertise it to the non-client. So the prefix will be advertised to here and the prefix will also be advertised to here. So client to non-client routes are going to be reflected. This is the rule that they follow. So what we should do, we should configure route number 2 as the route reflector so that it reflects the route from here to here. Also, I should configure this as the client so that the routes it receives from here also gets reflected. Now, the problem is that I need to go on route number 3 also. And this route number 3, I need to configure as a route reflector for this client. So this I need to mark as client. So route number 3, I will go on route number 3. I will say neighbor IP, and route reflector client. So this becomes server for this client, and this remains the client. Now it will receive the route from the server, and it will advertise it to the client as well. And this process can keep going on and on and on if you have multiple devices. This is how the route reflector works. The problem with the route reflector is that if there are many devices, then we need to configure like all these devices as the route reflector, which again, loops will not occur because in route reflector we have, whenever the route reflector reflects the route, it adds something called originator ID and something called cluster ID as the attributes in the prefixes that it has reflected. Originator ID is the router ID of the router that has originated the route into the network, and cluster ID is just like the AS path list. We have this concept called cluster ID. Cluster ID is the ID of the router reflector. It will be default like router ID, otherwise we can configure it as per our requirement as well. So there will be a list of these cluster IDs in the prefix as well, such as if the router 1 has reflected the route and it has the router ID as 1.1.1, it will be mentioned as 1.1.1.1. If you have changed the cluster ID by yourself, then that ID will be written down here. Then the route went to route number 2, and route number 2 was also the route reflector, so its cluster ID will be added in this cluster list as well. So using the originator ID and the cluster ID or cluster list, if I say, loops are prevented in the route reflector environment. If a router receives a route and it sees its own router ID as the originator ID, it will not accept the prefix. If the router receives a prefix, if a router receives a route and the cluster list, in the cluster list, it sees its own cluster ID, then it will of course not accept that prefix. Right, so we have this concept of cluster ID and originator ID to prevent any potential loop in the route reflector environment. However, the problem remains the same. If there are a lot of routers, we might need to configure many route reflectors in the environment. Typically 1 or 2 route reflectors you will see in an IBGP environment. So we have like 2 routers acting as the route reflector, and all these rest of the routers, all these routers that we have, all these routers will form the neighborship with these routers. They will advertise their routes, and these routes will get reflected to the other devices. They can also connect to the external network as well. So everyone is supposed to, form the neighborship with the route reflector, and the routes gets advertised via them towards the other devices. So in a large environment, like where configuring route reflector might not be a very good idea, we can also go for configuration. Configuration comparatively, is simple as compared to the route reflector. However, it is suitable for a fresh deployment. What happens in the configuration, if we have like an autonomous system configured and we have a lot of routers such as router 1, router 2, router 3, router 4, router 5, router 6, like a lot of routers are there. What we can do, we can configure these routers in sub-autonomous system. Like we can create within the autonomous system, we can create sub-autonomous system. We can configure like 2 routers in one sub-autonomous system. We can configure 3 routers in sub-autonomous system. I will say this is sub-autonomous system number 1, this is 2, this is 3. So here config IBGP, config IBGP, config IBGP, config IBGP, and here config EBGP. EBGP rules will be applied to advertise the routes from one point to other point. So in configuration, we break a big autonomous system into small autonomous systems. However, in case of route reflector, the AS remains as it is. We just configure 2 routers or maybe more than 2 routers to reflect the route from one IBGP neighbor to another IBGP neighbor. Configuration Here, configuration can also be used with the route reflector, such as here, config IBGP, routes received from one of the IBGP neighbor will not be advertised to the IBGP neighbor. So we need to configure it as the route reflector as well. So we can use like both at the same time as well. So these are some general, differences between the route reflector and configuration. Based on the requirement, either the companies can go for the route reflector, or they can, if they have like big network, or maybe there were multiple organizations and some sort of merger has happened. This was part of AS10, this was part of AS20, this was part of AS30. They all has formed some sort of, BGP neighborship and all. So a merger has happened and all of them now belong to a same autonomous system, BGP, let's say, for example. We can migrate from one autonomous system to other, but if it is not possible, we can make them part of a confederation autonomous system such as Hybrid. So this is going to be the main autonomous system, and these will be considered as the sub-autonomous system in this case. So different approaches we can take to configure the sub-autonomous systems in confederation environment, or we can simply configure the route reflectors. Next question here is that we need to implement BGP route filtering to restrict the routes advertised to a specific BGP neighbor, describe the different techniques and use cases and advantages, disadvantages, right? So we have a router that is connected into one of our autonomous system, and it has formed the BGP peering with some other routers, maybe in the same autonomous system, maybe in different autonomous system. Could be like AS200, AS300, could be like in the same AS as well. And we are advertising certain prefixes to these devices, and we need to control the prefixes. We need to limit the prefixes that we are advertising. So what techniques are available? The basic technique that is available, the most common technique that we can use is to use the prefix list. What we can do, we can go on our router number 1 and we can match the prefixes that we want to advertise. We can match the prefixes that we want to deny, like we don't want to advertise. We can permit, we can deny the prefixes that we want to permit or deny in a prefix list, and then we can apply that prefix list in the outbound direction with the particular neighbor. So we are going to create the prefix list, IP, prefix list, name, then permit or deny, then whatever network you want to permit or deny, and then we can apply that prefix list with that particular neighbor router. It is easy to configure. It is very easy to configure. It is very easy to manage. We get the control on what prefixes we can advertise or what prefixes we cannot advertise. It's very easy. And we can use the same prefix list like, on different tasks such as, for example, path manipulation. However, the disadvantage with this prefix list concept is that we cannot actually, do very robust matching. For example, we wanted to only advertise even prefixes to here, odd prefixes to here. That kind of thing is not possible in the prefix list. Second technique that we can use is called the access control list, or ACL. We can use standard or extended ACL. We can match based on source IP. We can match based on destination IP. We can control what prefixes I want to advertise to what neighbor. We can create the ACL. We can define the parameters in the ACL, and then we can apply that exactly the same way as we apply in the prefix list for the neighbor in out direction. With the help of ACLs also, we can actually configure route filtering in case of BGP. However, prefix lists are much more common as compared to the ACL. When we just want to filter basic prefixes, like we can match that even odd prefixes. Like we can match if a prefix has an odd number in the 3rd octet, then I want to advertise it. If a prefix has an even number in the 4th octet, then I want to advertise. We can do that kind of matching in access control list. So we get much more better control for this thing in ACL. However, in the prefix list, we can match and permit or deny prefixes based on CIDR, which we don't get actually on here. So both the techniques has its own advantages and disadvantages. And the best of them all, we can use this concept called route map. Very popular, very commonly utilized concept in BGP. We can use route map to perform path manipulation. We can use the route map to perform filtering as well. So route maps are more like, if else condition statement. So if this condition matches, then take this action. Else, if this condition matches, then take this action. Else, if this condition matches, take this action. So route map is more like an if else concept. In this way, we can define like, okay, what conditions to match and then what prefix needs to be advertised and block. In the route map, we can match prefixes based on ACL. In the route map, we can match prefixes based on the prefix list. In route map, we can match the prefixes based on other criteria, such as, for example, AS path list, community list, community tags. We have a lot of criteria based on which we can match the prefixes and block them in the route map, which is like much more better option as we get in the ACL or prefix list. And anyway, we can use ACL and prefix list in the route map as well. So route map is much more commonly utilized technique to perform path manipulation and filtering. We can use these AS path and community filtering separately as well. We can use like AS path ACL to AS path access control list to perform the filtering. We can also use this thing called community, which is more like a tag, community list based filtering we can also perform. So AS path ACL we can create. This ACL is going to match the prefixes based on the AS number in the AS path list, and it can permit or deny based on the same. And the community list is going to match the prefixes based on the tag, the community tag that we can set as per our requirement. Based on that, we can also perform the filtering. In AS path filtering, if you use AS path filtering, it becomes easy to filter the prefixes just based on the AS number. So if I am advertising the prefixes to this neighbor, these are the only, this AS, then these are the only prefixes that I'm going to advertise. And if I'm advertising the prefixes to this AS, then these are the only prefixes that I want to advertise. Those kind of thing, that kind of thing is possible in the AS path access control list. Community list is more like a community is a tag that we actually add onto the prefix. Communities, we have like well-known community, we have defined community. In the well-known community, we have like no advertise, no export, local AS, like internet. We have different well-known communities. Then we have normal tags such as 100, 200, 300, just normal route tags that we have in a typical IGP routes as well. So those things we can add a tag into the prefixes, and then based on that tag we can permit or deny the prefixes as well. So community based tagging can also be done in the border gateway protocol. We can also control like how many maximum number of prefixes we can advertise to the neighbor. We can control like on per neighbor basis, we can control like, okay, this is the maximum number of prefixes that can be received from a particular neighbor. I can go on the neighboring device and I can configure that this is the number of prefixes that I am supposed to receive from this neighbor. And if I receive more than that prefixes, either I'm going to, tear down the neighborship, reset the neighborship, or I'm going to give a warning or something like that. So these are some common techniques that we can use to perform route filtering in border gateway protocol. Each of these filtering techniques has its own advantages, disadvantages. So one must choose a proper route filtering techniques as per their use case. So the next question that we have here, it is you are configuring BGP committees to control path selection and policy enforcement in your network. Describe the concept of BGP committees and provide example on how you use them. So communities, like in case of BGP, communities act as a tag, such as, for example, in other protocol, in other IGP protocol. Let's say, for example, there is a route and that route needs to be advertised to the next router. What we can do, we can add a tag to that particular route, so that it could be easy to identify that, okay, this subnet has this particular tag value, and later on maybe we can block or permit the route based on that tag value. So we have n number of prefixes. These prefixes are getting advertised to router number 2, and router number 2, while these prefixes are advertised to the router number 2, they are tagged with the number 100. So it basically means like when the prefixes will be received on that neighboring router will receive it along with a tag value. That tag value will be used to actually identify those prefixes, and later on we can also perform some policies based on the same. Right. Now, the same tagging concept in case of BGP is known as the community. We can tag the prefixes with the help of community in case of border gateway protocol. So again, communities are the tags. Communities are just tags that we can add into the prefixes in border gateway protocol. Now, there are two types of communities here. We have standard communities and we have extended communities. In the standard community, we have like well-known communities, and we have defined communities or private communities. So well-known communities are more like well-known tags. Well-known communities are like well-known tags. Standard well-known communities, these are like standard tags. There are 4 tags under this: internet, no advertise, no export, and local AS. These are the names. So what do? You create a prefix list. In that prefix list, you match the prefixes in which you want to add this tag. Then you create a route map. In that route map, you call that prefix list, and then you set community, internet, no advertise, no export, or local AS. And then we apply that route map for the BGP neighbor. Now what happens here once we do that, once we advertise a prefix with the community, what exactly happens here? What will happen here is that your border gateway protocol, your BGP protocol will advertise the prefixes with the appropriate community tag that we have set. So for example, like router 1 is going to advertise these prefixes with the community tag internet. These are 3 prefixes. These 3 prefixes will be advertised to router number 2 with the help of community tag internet. What does this community tag internet means? Community tag internet basically means that the neighboring router can receive and advertise these prefixes to everyone, which is more like the default behavior that we have actually in border gateway protocol for the prefixes. So internet tag basically means that we are going to advertise the prefixes to everyone. That is what we receive. That is what we mean by internet tag. Okay. Neighboring router will receive those prefixes. Then the neighboring router is going to advertise those prefixes to all the neighbor router. Okay. We can also, instead, if we don't want the neighbor to advertise these prefixes to everyone, we can set other tags as well. Apart, like instead of advertising internet tag, what we can do, we can add no export community tag in case of BGP as well, or no advertise, no export. Those are like other, for example, tags that we can choose from. If we, for example, add no advertise tag, no advertise, as the name suggests, if you are advertising the prefixes with the keyword no advertise. No advertise basically means that the neighboring router will not advertise this prefix to anyone. Neighboring router will not advertise this prefix to anyone. No advertise means don't advertise it to any neighbor. No matter if it is eBGP, no matter if it is I-BGP, it just doesn't matter. You are not going to advertise this tag to anyone. Okay. So this is like no advertise. What else we can have? We can add a tag while advertising the prefix as no export. No export basically means that we are not going to advertise this tag. We are not going to advertise this tag to any eBGP neighbor. No export. That means I'm not going to export it outside my autonomous system. So I am going to receive it. I will advertise it to all of my iBGP neighbor, but I'm not going to advertise it to everyone. I'm just going to advertise it within the autonomous system, but I'm not going to advertise it outside the autonomous system. That is what we mean by no export. No export basically means don't advertise it outside the autonomous system to any BGP, eBGP basically neighbor. Right? Now, in no export, the prefixes will not be advertised to the real eBGP neighbor, but if we have used the concept of confederation, and this is my confed eBGP, this is confederation, and this is my confed eBGP. In that case, the prefix will be advertised. If you don't want to advertise the prefix even to the confed eBGP, in that situation, what you can do, we can actually configure this option called local AS. Local AS basically means that I am not going to advertise it. Local AS basically means that I'm not going to advertise it outside even the local autonomous system. That means I will receive all these prefixes. I will advertise it to my confed iBGP, but I'm not even going to advertise it to the other eBGP neighbor, no matter if it is real eBGP or if it is confed eBGP. So local AS. These are four well-known committees like Internet, no advertise, no export, and local AS. Internet means advertise it to everyone. No advertise means do not advertise to anyone. No export means do not export it outside the autonomous system. And local AS means do not export it outside the local autonomous system. Just advertise it within the local autonomous system. These are called well-known committee tags that we can set on the prefixes, and we can control what prefixes neighbor can advertise it to the other router or what prefixes it cannot advertise it to the other router. Apart from having these well-known committees, we also have defined committees or private committees. These are just tags. Just like we have route tags, these are just tags. Such as, for example, when router 1 advertises the prefixes to router number 2, it will add the tag as 1:1 x:y format. I can add the tag in the xy format, or we can add the tag in a simple numerical number format such as 100, 200, whatever. So either we can add the tag in this format, x:y format, or we can add the tag. This is the new format, this is the old format. IPBGP community new format is a command that we can use to change the format from old to new one. But the point remains the same. These are just numbers. These are just tags that we can add onto the prefixes as per our requirement. And later on, we might want to perform the filtering as per the requirement as well. Later on, we might do filtering as per our requirement as well. Okay. Now, both the committees come under the standard committees. In the standard committee, we have well-known committees and we have the defined or private committees. Now, apart from that, we also have extended committees. Extended committees such as, for example, in BGP, we have this thing called cost committee. Here we have things such as, for example, site of origin, route target. Like we have different extended committees as well. BGP can add extended committees wherever it wants. We can add the extended committees as per our requirement onto the prefixes, but BGP can also add extended committees as like it wants. Right? So, such as, for example, when we use BGP in a MPLS service provider environment, we will notice that that route target extended committee will automatically get added in the border gateway protocol. Similar to that, when we configure BGP in our SD-WAN environment, then we will notice that the site of origin committee will be added automatically in that. Point is, BGP can add these extended committees automatically, or it can also add, we can also add the committees as per our requirement. Right, so BGP supports a lot of extended committees as well, such as, for example, route target extended committee. We have like extended committees for traffic engineering. We have like other committees such as site of origin. We have other committees such as, for example, cost committee. We have different like BGP committees as well. So based on your requirement, you can create your, you can add the tag onto the prefixes when it is advertising to the neighbor router. And then we can match these prefixes based on the community list. We can create a community list just like the ACL prefix list. In BGP, we have this concept of community list. So in border gateway protocol, we can configure the BGP community list. In that community list, we can match the prefixes based on the community tag that we have added. Then here we have like a standard community list. Here we have expanded community list. In the standard community list, we can use like, we can match the committees based on the number or the tags that we have configured. In the expanded community list, we use the concept of regular expression. So we will create the community list. In the community list, we can match the prefixes based on the community tag that we have added. And then we can either use it for like path manipulation in the route map, or we can use it for route filtering in the route map. So you can create a route map, Cisco match community and the list, and then you can define like you want to deny or you want to permit in the route map statements itself. So we can use the BGP committees to control like what path is going to be the best path, what path is going to be the backup path, or we can control like, for example, this prefix is allowed, this prefix is not allowed. Right, so that also comes under the committee list. BGP committee list allows us to control. BGP committee list allows us to control like what prefixes can be received, cannot be received, or what is going to be the best path, backup path, and all those things we can control based on that committee list. Commands are simple, like first create the committee list, then create the route map. In that route map, match the committee list, and then either set the attributes, change the attributes, or perform route filtering based on the same. So these are the ways by which, like, we can use the committees to control path selection and policy enforcement in the network. We can control like, okay, this subnet you are going to receive, but you are not going to advertise it to anyone else. That can be done, for example, with the help of these committee. So next question that we have here, it says that your network is expanding and you are planning to implement BGP route summarization or aggregation to reduce the size of the routing table. Explain the benefits, challenges associated with the route summary, aggregation, and summarize the steps required for the implementation. So what is route summarization or aggregation? We call route aggregation in case of BGP. Normally we call it like summarization. So let's say, for example, a router is receiving n number of prefixes. It can advertise all those n number of prefixes to the neighbor router. However, the neighbor router is running low on resources. It might not be able to handle those much of routes in its topology table, database table, or the BGP table. Here, since we are using BGP, I would say BGP table. So the problem is, the challenge is that we want to make sure that this router is able to reach to all these networks while maintaining the least number of routes possible in the network, in its table, such as BGP table and the routing table. I don't want to break my connectivity from router number 2 to this destination. I want that this router should be able to reach on there, but I don't want to maintain all these routes in the routing table. So one way to achieve it is to go on the router and configure this thing called route summarization or aggregation in case of BGP. Let's say, for example, these are like 10.1.1, 10.1.2, 10.1.3, goes up to like 10.1. Let's say, for example, 15. So instead of advertising all these 15 number of subnets to the neighbor router, what we can do, we can advertise just one simple subnet, 10.1.0.0/16 to the neighbor router. This is not a correct, this is not an exact summary of these prefixes, but it does cover all these prefixes in this address. Router number 2, instead of receiving these 15 prefixes, it will now just receive one subnet. That one subnet will require less number of resources to be maintained in the BGP table and the routing table. 10.1.0.0/16, for example, is the subnet that is getting advertised from router 1 to router 2. And since this route that we are receiving from the neighbor router, it covers all these destinations, I will still be able to reach out to each and every destination. However, I don't have exact route to reach to those destinations, so I will not be able to do any path manipulation. I will not be able to do any route filtering. Those capabilities we will not have because we are not actually receiving all the routes information as it is. Either the entire summary will be received or the summary will not be received. You will be able to perform the path manipulation for this route. You will be able to restrict the advertisement of this route, but you will not be able to do anything on these individual prefixes. That will be a limitation. However, the resources required to maintain this prefix information will be comparatively very low as compared to these ones. So route summarization is a concept of advertising a summary route to the neighbor router instead of advertising all these routes as it is, so that the reachability is still there and the amount of routes that the router needs to maintain is low. So to reduce the size of the routing table, we can configure this BGP route summarization. Now in BGP, when it comes to route summarization, some other concepts are also supported, such as, for example, while advertising the summary address to the neighbor router, I can use different types of maps. Command is very simple. Just go under the router BGP and then use the command aggregate address and then whatever summary you want to configure. Aggregate -address and then configure whatever aggregate address, network and mask, configure what you want to advertise. Remember that once we configure this command aggregate address, remember that the BGP will advertise summary as well as all the exact prefixes as well. This is the default behavior. Once we configure the aggregate address, BGP will advertise the aggregate address as well as the exact prefixes. We need to add the keyword called summary only. Once we use the keyword at the end called summary only, the advertisement of these exact prefixes will be suppressed. That means the advertisement of these prefixes will not be done. The BGP will only and only advertise the summary route. So summary only keyword is one additional command that we can actually configure after or at the end of the statement. Apart from this summary only keyword, remember that when the BGP creates the summary address for these prefixes, it will not copy the AS path information in that. We can also use the keyword called AS set so that the BGP adds the AS information in the summary address when advertising it to the neighbor router. Because otherwise, if the same summary address comes back to me and I receive it blindly, I accept it blindly, it might cause a loop in the routing network. So I don't want that to happen. So I can also use this additional keyword called summary only. So we have summary on, we can add this keyword called AS set. So we have AS set, we have summary only, we have two additional keywords after this aggregate address command that we can actually have. Apart from that, we can control what prefixes we want to suppress. Suppress map. We have this concept of suppress map where we use a route map to control, to add, to match what prefixes we actually want to add, what prefixes we actually want to suppress with a neighbor router, right? So suppress map that we have here, suppress map is there to control. At the end of this, we can use the keyword called suppress map. There we are going to reference a route map. In that route map, I will mention what prefixes we want to suppress. Suppress map is there to control what prefixes, out of all these prefixes, what prefixes will be suppressed and rest of the prefixes will be advertised as it is. We also have unsuppress map. Unsuppress map basically means that I can control that the router is going to suppress means stop the advertisements of all these prefixes, but it is going to unsuppress. It is not going to suppress this exact subnet. So unsuppressed map can also be configured. Unsuppressed map can also be configured. We have other maps such as, for example, attribute map. Attribute map is to change the path attributes of the summary address, like the summary address that we are advertising. To change the attribute of that summary address, we have this concept called attribute map. We also have like advertise map. We advertise map basically means that let's say, for example, I want to advertise the attributes of this subnet in that summary, so that I can match in the advertise map as well. So advertise map means like I want to advertise the attributes of a particular prefix in the summary address. So that is what we are going to refer to as the advertise map. So we have additional concepts on the inside the summary address, within the summary address concept. Additional concepts such as summary only, AS set, suppress map, unsuppress map, advertise map, attribute map. These are different concepts that we can implement along with the route summarization. Right. So there are a lot of benefits, as you might have understood by now, that instead of advertising all the prefixes as it is, since we are only advertising one summary address, that summary address will require less number of resources in the BGP table, in the routing table. So it will save some resources. And however, the challenges will be like, since we are not receiving the exact prefix information, path manipulation, those things might not be possible. How to configure? So first of all, find out the prefixes that you want to summarize, such as, for example, 10.1.1, 10.1.2, 10.1.3. Second, create a summary for that. Use the concept of network and subnet mask. So create a summary address for that, 10.1.0.0/22. Configure the summary address for the same. Try to match these prefixes as many prefixes that you can match in the summary. So for example, 10.1.0.0/22, it will match like these three prefixes, and then use the command like aggregate address. Aggregate address command you can use in the router BGP configuration to actually advertise the summary address to the neighbor router. In addition to that, we can configure things such as, for example, summary only, AS set, suppress map, unsuppress map, advertise map, attribute map. These are the additional things that you can add on along with the aggregate address syntax. All right, so next question here that we have is that we want to implement BGP, route redistribution between BGP and IGP within the autonomous system. What precautions should you take to avoid any potential routing loop and ensure a stable network? Right, so question says that we might be running some IGP routing protocol such as OSPF or AIGRP in the internal network, and we might be connected to one or maybe two external network with the help of border gateway protocol, BGP, could be eBGP. And here we want to make sure that these prefixes that we have and these prefixes that we have, they get mutually redistributed without causing any loop. Topology can be a little bit different. As per the scenarios, you can have the different topology. So when it comes to like route redistribution, one thing you must understand that when BGP redistributes any IGP routes into it, such as, for example, when we go under the router BGP process and we use the keyword redistribute and we redistribute protocols such as OSPF or AIGRP, those prefixes will be redistributed with the origin code of question mark. which indicates that unknown heritage. It is just to indicate that the prefix is basically being redistributed. Also note that BGP is going to copy the metric value of the IGP while doing the redistribution. So if, let's say, for example, a route has the metric value of 10 in IGP, when it gets redistributed into BGP, it is going to copy that metric value. And in the reverse way, like when the BGP routes are redistributed into the IGP protocol, such as OSPF or EIGRP, we do need to confirm router OSPF, redistribute, BGP, and we can define the metric type, and all the additional commands that we have. Similar goes for like EIGRP. If you are redistributing under router EIGRP, redistribute BGP metric, bandwidth, load, delay, reliability, MTU, all those settings in a correct order you need to define. Now the challenge is that when we have single redistribution point, then there is no problem actually. But if we have like multiple redistributing point, chances of loops are there. All the routes that are redistributed from BGP to IGP, they might get reverse redistributed and cause a potential loop, because at the end, like, all these ISPs are interconnected, so they have all the route information. So what we can do, we want to make sure that in our autonomous system, if we have like multiple entry exit points, and we have, let's say, for example, 1 or 2 ISPs, completely our design, I want to make sure that all the prefixes that get redistributed into the IGP, they do not get redistributed back into the BGP. And there are a variety of things that we can do. One thing that we can do is to basically tag. Once you are redistributing the prefixes from BGP to IGP, you can tag those prefixes. Tag is just a number. We can tag those prefixes with a particular any number. And when the redistribution is done in the reverse order, when we are redistributing from IGP to, let's say, for example, BGP, we can filter the prefixes based on that tag value, so that all the prefixes that I have advertised will not be received to me from any other path. Some sort of route redistribution policy we are going to configure. We are going to implement some route filtering policy. We are going to control that all the routes that I learn from BGP to IGP, they are not reverse redistributed from IGP to the BGP. Right? That is one thing you need to understand. Also, we can have like I-BGP in the internal network. Like we can have internally, we can have things such as here, we can have I-BGP here. Here we have I-BGP, and maybe after that we are running some OSPF or EIGRP IGP instances. We have here like IGP, and here all the way we are having BGP. So these routes are being learned. Now this time the redistribution is not required from BGP to BGP. So all the routes that you will learn, these routes will be advertised to this next router. This router can be configured as the route reflector so that the routes get advertised to here. Remember that BGP does not redistribute internal routes. By default, BGP does not redistribute internal routes. All the routes that the BGP has learned from the I-BGP, it is not going to redistribute into the IGP protocol. So all the routes that you might have learned, these routes will not be redistributed into the IGP. BGP is not going to redistribute internal routes into IGP. So additionally, what you should do, you can use the command BGP redistribute internal. You need to make sure that this command is running BGP redistribute internal. This command tells the BGP router to redistribute internal prefixes into the IGP protocol. That is also one thing you need. So the main point is that if the redistribution has to be done from IGP to EGP, what we can have here, we can apply a variety of route filtering policies. If you have single redistribution point, then it is not going to be any problem. But if we have like multiple redistribution point, we should make sure that all the routes that we have learned must not get reverse redistributed, and we can use techniques such as, for example, route filtering. We can do the filtering based on tag, we can do the filtering based on the metric and other parameter. So different options can be there that you can opt for, and you can control like what routes should be redistributed, and those routes should not be reverse redistributed into the origin protocol. Otherwise, routing loops might occur. Right, so next question that we have here, how can I announce a prefix conditionally to one ISP only when I lose the connection to my primary ISP. So the scenario is something like that. Here we have like one router in our autonomous system, and this router is connected to multiple ISPs. It is connected to, let's say, ISP1, and it is connected to ISP2. This router is advertising a few prefixes such as A, B, and C to ISP1 and to ISP2. Based on that, these ISPs are choosing, let's say there is a user, there is a network where some users are there. These users are deciding that if they want to reach to this destination, the traffic might go from ISP1 or ISP2. So what they want to do, they want to actually advertise these prefixes to another ISP only when the connection to the primary ISP has gone down, which is a common thing to do if you don't want to use any path manipulation techniques. Because if I advertise both of the prefixes and I want to choose that maybe this point should become my preferred entry point in my autonomous system, then we can advertise higher or more number of ASs from here, low number of ASs from here. We can use variety of attributes to influence best path selection in case of BGP. But here we don't want to use best path selection in case of BGP. We are not even going to advertise the prefix to the neighbor router until our main ISP goes down. And if I am not even advertising my prefixes to one ISP, these devices will never be able to reach to my destination via that ISP. So that is what we need to control. We need to control here. We need to fix here. We need to use a method. We need to discuss a method that we can use to announce the prefixes to one ISP only when the reachability to the other ISP has gone down. So we have an option here. The option that we get here in case of BGP is referred to as exist, like concept is advertise map. There is a concept in BGP referred to as advertise map. Advertise map allows the router to advertise certain prefixes based on condition. Conditions can be defined in exist map, or condition can be defined in a non-exist map. So advertise map is a concept in BGP that allows us to control what prefixes can be advertised to the neighbor router. And this advertise map is going to use the concept of exist map and the non-exist map. Exist map basically means when the certain conditions meet, such as, for example, a certain subnet is present in my BGP table, then only I am going to advertise the prefix to you. And non-exist map basically means that if a certain subnet is available in my BGP table, then I am not going to advertise the prefixes to you. So we can put the conditions. We can put the conditions based on this thing called exist map and non-exist map to control what prefixes can be advertised to the neighbor router. Right? So what I can do here, I will create an advertise map. Basically, advertise map is just a route map. So I'm going to create a route map. In that route map, I'm going to match all the prefixes that I want to advertise. And this is what we are going to refer to as the advertise map. Then I'm going to create again one more route map, and this route map is going to match our condition. It could be existence of a subnet, or it could be non-existence of a subnet. So for example, I can say, let's say for example, this service provider router is advertising me a certain subnet information. The subnet is, let's say for example, D. As long as this subnet exists in my BGP table, I will consider that there is a complete reachability between me and this provider. As a result, I am not going to advertise any of my prefix to another ISP. So I will create an exist map, which is eventually a route map. In that route map, I'm going to match that particular subnet. Subnet means here the subnet was, let's say, D. This subnet is being advertised from the ISP router. Now, as long as this subnet exists in my BGP table, I am not going to advertise any subnet to the I am not going to advertise any route to the neighbor router. I can do that. Or as long as this a subnet exists in my BGP table, I'm going to advertise everything to the neighbor router. Up to you. We can use the same subnet information. We can use this route map as the exist map or the non-exist map. Exist map basically means if this subnet exists, then I'm going to advertise the prefix information. And non-exist map basically means that if this subnet exists, I am not going to advertise the prefix information. So in our case, what I'm going to do, I'm going to apply a non-exist map. Non-exist map basically means as long as this subnet information is received to me, as long as I am receiving this subnet information, I am not going to advertise the prefix to the neighbor router. So advertise map is going to match our prefixes that we want to advertise, and non-exist map is going to match the condition being that if certain subnet exists, I am not going to advertise the prefixes to you. So as long as my connection to this ISP goes down due to any reason, I will no longer receive this subnet information in my BGP table. And if this subnet does not exist, that means I am going to advertise all these prefixes to the other service provider so that they can reuse this path to reach to me. This kind of thing we can actually control with the help of this exist map and non-exist map. Right, so in order to achieve this task, how can I announce a prefix conditionally to one ISP only when I lose the connection to my primary ISP? We can use the advertise map along with the exist or non-exist map to achieve this particular result. Right, so next is explain BGP route dampening mechanism and its use cases. So let's say, for example, we have a certain network running behind this router, or multiple networks are here, network A, B, and C. These prefixes are being advertised via border gateway protocol to the next router. From here, it is being advertised to outside network to variety of. Now the point is everything is working fine. We can do ping, trace, and everything is okay. Suddenly what happens, due to any reason, this prefix starts, like this subnet starts flapping. This prefix is flapping. This subnet, this network is basically coming up, going down, coming up, going down again and again. In every, let's say, for example, 5-10 seconds, the subnet comes up, goes down again and again. Now the problem is, anytime the subnet goes up or goes down or comes up, this device is going to generate a BGP message. That BGP message will be sent to the next router. From this router, it might be sent to the next devices such as ISP, and this update might flood in the entire network on the internet as well. So if, like, repeatedly, if the changes are happening, subnets are coming up and down, it will have a lot of like negative impacts. It will impact the network stability. This change, the link has come up or gone down, this will ripple through the entire routing table of the internet as well, which will again cause high CPU utilization. It might cause high CPU utilization and resource utilization as well. So what I want only when the subnet goes stable, only then this prefix should be advertised to the neighbor router. Otherwise, this should not be advertised to the neighbor router. So what we can do, we can enable this feature referred to as BGP dampening. BGP dampening. I can enable this concept called BGP dampening. Once we enable the BGP, it takes some time. Once we enable the BGP dampening, it will take some time. But once we have enabled the BGP dampening, what will happen? Let's say this subnet is up. All these subnets are up. Prefixes are getting advertised to the next devices. Everything is okay. Let's say, for example, the subnet has gone down. That prefix will no longer be advertised to the next routers. But this router is going to create an entry. This router is going to maintain this information that the prefix has gone down. This prefix, once it goes down, this prefix has gone down, it will be imposed with a penalty of 1000. A penalty will be added onto this subnet. As soon as it flaps, a penalty is going to be added onto this particular subnet. A penalty of 1000 is going to be added. It is just a numerical value. It just represents a penalty being imposed onto that particular subnet. Okay. then this penalty keeps reducing gradually throughout the time. So it is 1000 now. After some time it will be 997, then 996. It will keep decreasing, like, gradually throughout the time. Now again, after some time, the prefix came up again. The advertisement, the router starts advertising that prefix to the neighbor router. Everything is okay. Again, this prefix has gone down. Once this prefix has gone down, this device is going to add the penalty by 1000 again. So penalty became like 2000, not exactly 2000, because this penalty was reducing gradually. So might be like if the penalty has been reduced to, let's say, 998 or 991, whatever. So the overall penalty is going to be 1991. So the penalty will be added by 1000. 1000 will be added into the penalty. Okay. Again, this prefix came up, advertisement. Again, the routers started advertising the subnet as it is to the next router. Now, next time, as soon as this subnet goes down, let's say this subnet has gone down again, this router notices that the subnet has gone down. It is going to again add the penalty. It will increase the penalty by 1000. Again, as you remember, this penalty will keep decreasing throughout the time. So there are chances that this will be like whatever, like you can consider whatever. Now the point is, after this much, as soon as the penalty crosses 2000, once the penalty, I'm specifically talking about Cisco devices. So when the penalty crosses the 2000 limit, even though this prefix has come up again, the advertisement of that prefix is going to be suppressed. Advertisement of that subnet is going to be suppressed. Advertisement of that particular subnet is going to be suppressed due to dampening. This prefix is basically damped. Now the router is going to wait. Router is going to wait for this penalty to go below a value called reuse limit. This is a value. This is again the value. Again Cisco iOS, it is 750. So it will now wait. It will wait for the penalty to go below 750, and as soon as, let's say, penalty goes to 750, then this prefix can be re-advertised to the neighbor router. So here we have this suppress penalty. This is what this 2000 value is what we refer to as the suppress penalty. Means if the penalty reaches to this value, the advertisement of that subnet is going to be suppressed. And every time a subnet flaps, a penalty of 1000 is actually added. There is also this thing called reuse limit. Reuse limit basically means, like, once the advertisement of that prefix has been suppressed, in that case, the penalty must go below this value, then only the advertisement will start again. Other timers are there as well, such as half time, max suppress limit, like for maximum how much amount of time the prefix can be suppressed, then also those things, of course, are going to be there. But overall, the concept remains the same, that I'm only going to advertise the routes that are stable. I'm not going to advertise the routes that are not stable. So configuring this route dampening will improve the stability of your network. It will only advertise those prefixes that are stable. It is going to suppress the advertisement of flapping prefixes. It will reduce the CPU and memory utilization, because since the changes, if the link comes up or goes down, if the subnet comes up or goes down, the advertisement is not going to go through the entire routing table if the advertisement has been suppressed. So unnecessary CPU utilization or memory utilization will not be there. Routes are not going to ripple through all the routing tables of the router, or the route oscillation is going to be like reduced as well. And of course, convergence is going to be improved. Like devices only need to converge when the advertisement has started. After that, every device can recalculate the routing table, BGP table. But since the prefix has gone stable, the advertisement will not be there, right? So these are some advantages. These are some advantages of using route dampening in our network.